Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on linear algebra, chapter Adjoint and Inverse of a Matrix. Lecture number 5, in which I will solve some more problems on adjoint and inverse of matrix. Now we solve a problem. Problem is, if the product of two non-zero matrices is a zero matrix, so that both of them must be singular matrices. Let A and B be two non-zero matrices. That is, A not equal to 0, B not equal to 0. This is number 1. But given that AB is a zero matrix, this is number 2. Case 1. Let A is non-singular, implies that determinant A not equal to 0. This 0 is real number. Implies that A inverse exists. This is number 3. Multiplying both sides of 2 by A inverse, we get A inverse AB equal to A inverse 0 matrix. Implies that A inverse A by associative law, B equal to 0 matrix. If we multiply any matrix with 0 matrix, that is 0 matrix. A inverse A is identity matrix. Multiply B equal to 0. I equal to identity matrix or unit matrix. Implies that B equal to 0. Identity matrix multiply B is B, which is against of number 1. In number 1, B not equal to 0. B is not a 0 matrix. Therefore, our assumption A is a non-singular matrix is wrong. Implies that A is a singular matrix. This is proved. Case 2. Let B is non-singular implies that determinant of B not equal to 0 implies that B inverse exists. Multiplying both sides of 2 by B inverse, we get AB B inverse equal to 0 matrix multiply B inverse equal to 0 implies that A B inverse equal to 0 implies that A B inverse is identity matrix. AI equal to 0 implies that A equal to 0, which is against 1. Therefore, our assumption B is a non-singular matrix is wrong. Implies that B is a singular matrix. Proved. Therefore, if A and B are non-zero matrices and AB equal to 0 matrix, then both A and B are singular matrices. Proved. Now we prove the next problem. Next problem is if determinant of matrix A equal to 0, then prove that determinant of adjoint A equal to 0. Now we prove this. Given that determinant of A equal to 0, this is number 1. Case 1. Let A is a non-zero matrix. That is A not equal to 0. This is number 2. Since we know that A adjoint A equal to determinant A multiply unit matrix I, this equal to determinant A equal to 0, 0 matrix multiply unit matrix, this is equal to 0. Implies that A adjoint A equal to 0. Let adjoint A determinant not equal to 0 implies that adjoint A whole inverse exists. Means adjoint A is non-singular, then its inverse exists. Let this is number 3. This is number 4. Multiplying both sides of 3 by adjoint A whole inverse, we get A adjoint A multiply adjoint A whole inverse equal to 0 multiply adjoint A whole inverse. This is a 0 matrix. Implies that A here adjoint A multiply adjoint A inverse means unit matrix. A multiply I, 0 multiply this any matrix is 0. Implies that A equal to 0. This is number 5. Therefore, 2 and 5 contradict with each other. Therefore, our assumption determinant of adjoint A not equal to 0 is wrong. Implies that adjoint A determinant equal to 0. Proved. Case 2. Let A is a 0 matrix. Therefore, A equal to 0. This is number 6. This is number 7. Therefore, each element of A be 0 implies that cofactor of each element will be 0. Let B be a matrix containing corresponding cofactors of each element of A. Therefore, B equal to 0 matrix, because value of each cofactor of each element of matrix A will be 0. Implies that adjoint A equal to transpose of B equal to transpose of 0 matrix is 0. Implies that determinant of adjoint A equal to determinant of 0 matrix equal to 0 real number. This is number 8. Therefore, from 6 and 8 we get determinant of adjoint of A equal to 0. Proved. Now we solve the next problem. Next problem is let B and C be two square matrices of same order and A be a non-singular matrix. Then prove that A multiply B equal to A multiply C implies that B equal to C. Given that A is a non-singular matrix, therefore determinant of A not equal to 0 implies that A inverse exists. This is number 1. Let A be equal to AC. This is number 2. Multiplying both sides of 2 by A inverse, we get A inverse AB equal to A inverse AC implies that A inverse A by associative law multiply B, here by associative law A inverse A C by associative law implies that A inverse A is unit matrix, identity matrix, IB equal to IC, I equal to identity matrix. Implies that B equal to C. Proved. Now we solve the next problem. Next problem is let A and B be two square matrices of order n if A multiply B equal to unit matrix, that is identity matrix, then prove that B multiply A is unit matrix, that is identity matrix. Now we solve this. Solution. Given that A and B be two square matrix of order n and A multiply B equal to unit matrix, identity matrix. This is number 1. Implies that determinant of AB equal to determinant of unit matrix. This is equal to determinant of A multiply determinant of B, and determinant of unit matrix is 1. Implies that determinants are real or complex number. So multiplication of two real or complex number is 1. Therefore this is not equal to 0. Determinant of A not equal to 0 and determinant of B not equal to 0 means non-singular. Implies that A inverse and B inverse exist. This is number 2. Multiplying 1 by A inverse, we get A inverse AB equal to A inverse unit matrix by associative law. A inverse A B equal to multiplying these we get A inverse associative law. This is A inverse A is unit matrix. Multiply B equal to A inverse implies that this is B equal to A inverse. This is number 3. Therefore, BA equal to B means A inverse A using theory. And this is unit matrix and proved. Now we solve the next problem. Next problem is A square matrix is non-singular if and only if there exists another square matrix B such that A multiply B equal to unit matrix, that is identity matrix. Now we solve this. Let A is a square matrix. Now let A is non-singular implies that determinant of A not equal to 0 implies that A inverse exists. Therefore, A inverse equal to unit matrix. Let this is number 1, this is number 2. Let A inverse equal to a matrix B. This is number 3. Using theory into we get AB equal to unit matrix or identity matrix. Proved? Conversely, let AB equal to identity matrix implies that determinant of AB equal to determinant of identity matrix implies that this is equal to determinant A multiply determinant B and value of this is 1 implies that determinant of A not equal to 0 and determinant of B not equal to 0 implies that A is non-singular. Proved. So, when we assume that A is non-singular, then A multiply B equal to identity matrix. And when we consider AB equal to identity matrix, then we prove that A is non-singular. Therefore, necessary and sufficient condition proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button, and if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.